So I just launched a website. It's a passion project of mine I've been working on for a couple of months now. Think about it as Letterboxd but for video games. It's a fantasy-inspired video game reviewing website where you can come on, review your games, and find new games to play. It's called GameWire.net. Link is on screen if you're interested. Now I've already launched the website and had some really good feedback so far, but there's one big issue that we need to solve today, and that is that the site can be really slow. And let me tell you what, slow websites are awful. I know I hate using them. And Amazon's even done some research to show that they can actually cost you revenue. This is something obviously we want to avoid. Unfortunately, I don't have any crazy observability tools like some companies do, so I'm going to try my best to show you the issue and explain how we can fix it. So on screen right now, I'm showing you a quick summary from my deploying tool about my response time. So those of you who don't know, P50 is your median response time, basically the average amount of time it takes for a user to submit a request and get the response to that. And for me, it's around 200 milliseconds right now, which is pretty bad. And what's even worse is that the 90th percentile, so the slowest 10%, is 400 milliseconds, reaching all the way up to 1500 milliseconds, which is absolutely awful. And for a more concrete example, I have my browser developer tools open right now, and I just ran the search endpoint a bunch of times. You can see I have horrible response times ranging from 1.5 seconds to 1.8, some are much quicker at 300 milliseconds, but this is pretty bad. And unfortunately, there's not much I can do to speed it up. Our database has over 500,000 games, and searching through is pretty intensive. So the way we're going to fix this today is by caching. So what's caching, you may ask? Let me explain with a series of poor diagrams and explanations. So here's a model representing how data flows between you, the client, and the server, and your database. So when you send a request to your server, the server calls its database, does some operations, some reading operations, some filtering, some math, whatever, and then it gives you that response. This can often be really slow. Now this diagram shows you the magic that is Redis and caching. Essentially, the client and server interaction stays the same, but when your server gets a request, instead of asking SQL every time, it would first go to Redis, hey Redis, have you seen this request before? And Redis would be like, yeah, I've seen it. And instead of actually going through your database, it would basically return a copy of the previous request with that information. So now when you search for Minecraft on our website, instead of your database doing all the heavy calculations, reading 500,000 games, and then giving you the results, Redis just says, hey, this is the search results of when a user searches Minecraft. And it's like magic because of how fast it is. In a project I worked on in the past, I implemented Redis on some of our endpoints there, and we cut down response times by 50 times. That's a crazy improvement, and I really hope I can achieve similar levels of improvement with GameWire. But there's one more layer of issues when it comes to caching. It's not just perfect magic. And that's a stale cache. Because we're not actually reading the database for any information, we're just passing on information that we've already seen and calculated. So what happens when the information that you calculated is no longer accurate? For example, on GameWire, what if we have a cache that represents your library of games, what games you've played? So every time you go to your hub, it'll show you, these are the games we played, we don't need to recalculate it. But what if I play a new game? Then my cache, basically my memory of what happened, and what's actually in my database is different. This is called a stale cache. And what you do to fix this is you invalidate your cache on operations that modify the data. So in my example, every time I review a new game, I would invalidate the cache. This would mean the next time I load up my homepage, I have to recalculate it, but from that point on, I'll have an accurate and fast representation of what my homepage should look like. So now that you know what Redis is, let's start actually implementing it. I'm going to start implementing it on my search API, because that's where I know that the biggest improvement will lie. And now it's time to ask my best friend for some help. So I'm going to use Codex to help write out all the documentation and the plans of how we're going to actually implement caching. To be honest, there's not that much to think about. If we reference our diagram, it really boils down to as simple as when your cache hits, you reference your Redis, and when it doesn't hit, we fall back to our database behavior. As for when we need to invalidate our cache, our database is provided by IGDB. I really don't know how often they update their databases, but in our use case, games don't come out every second, they come out daily or maybe in the middle of the day. So in our case, I think a 12 or 24 hour time to live for each cache seems pretty reasonable. And at the end of that time, it'll auto refresh. So I'd like to show off the plan that Codex helped me make. And after basically a 40-minute session of asking Codex questions, reviewing documents, testing the actual implementation, and going back and forth with it, we have caching on our website. I think I would like to drop a video explaining how I use Codex and Claude Code to help ship solid code, because I think I actually have some elite ball knowledge on how to get the best out of it. So let's review the results in some crappy live demo I recorded last night. Okay, so Redis should be all set up now. If you go to the search page and let's open up our DevTools, we should be able to see the API calls that happen when we type something in. I'm going to type out Fallout 4. And you can see that is slow. It took 1.52 seconds for Fallout 4. Now if I were to preserve the log so we can see, refresh the page, and it's completely clear, type out Fallout 4 again, and boom, 15 milliseconds. So now when anybody type out Fallout 4, they're going to have really quick responses. And anytime a new game is added, we'll have to go through that really slow response, but again, for every other response again, we're gonna have that really quick, fast response time. Yeah, sorry for that live demo, but the results speak for themselves. As you can see on your screen, the very first search result is when our cache misses and we have to recalculate it, but every subsequent search is a cache hit, and you can see the reduction in latency from 1.5 seconds all the way down to like 15 milliseconds. Although this might be an extreme or outlier scenario, that is 100 times improvement in response time. So I continued down this road and had Codex design caching for some other routes like the games library. And unlike the search page where we can just like invalidate on like a time to live basis, for games library we actually need to invalidate your cache on write. So like I said earlier, when you like make a new game review or import from Steam, we need to like invalidate your previous cache and write you a new one. And while on my small meager game library, I don't see a big improvement. People with hundreds of games in their Steam library or hundreds of games that they reviewed will definitely see an improvement in response time and loading speed of their library page. So now it's the next day, and I want to share some results of what caching has actually done measurably. Now, it's definitely not the most scientific test. I don't think we have enough data to like 100% say that we have an improvement. This could just be a fluke because it's over the course of like 12 hours with very limited traffic. But I can't lie, the results are looking pretty good so far. If you compare it to what we had yesterday before we implemented caching, we had a P50 response time of like 400 milliseconds, versus now we have a response time of like 52 milliseconds, which is like a 4x improvement, which is really, really good. Well, that's kind of all I have for my very first devlog. I hope someone out there actually enjoyed this video. I actually had a blast making it. I actually used to make a lot of videos like this back in high school, so it's really nostalgic for me to open up Audacity and open up DaVinci Resolve one more time, but it's time to talk about something related to my career. That's all I have. Thank you and goodbye.